On May 15, 2001, a train nobody was driving tore across Ohio for 66 miles at nearly 50 miles per hour. CSX 8888. 47 cars, 2 loaded with molten phenol, rolled out of a Walbridge rail yard under full throttle after a routine repositioning move. Every safety system designed to prevent this was in place. Not one engaged. The reason starts with something no one thought to question. Walbridge Yard, just outside Toledo, Ohio, starts most days with the same routine: switch lists, radio chatter, and the slow shuffle of freight cars between tracks. On May 15, 2001, CSX Locomotive 8888 was scheduled for a short move, just repositioning a string of cars to clear space for the next outbound train. The assignment looked ordinary on paper. The yard crew, working under job code Y11615, had already spent the morning shifting cuts of cars between the yard's 12 tracks, following a schedule built to keep the line moving and avoid bottlenecks. By midday, the train master called for a new move: assemble 47 cars, including 2 tankers of molten phenol, and push them toward the departure yard. The engineer climbed into the cab of 8888, an EMDSD-42, and lined up for the move on track K12, a routine that had played out thousands of times before. The plan was simple: ease the throttle up, use dynamic braking to control speed, and nudge the cars into position. The yard's geography demanded careful handling. Tracks crisscrossed, switches waited for the right alignment, and every move depended on split-second decisions. The engineer set the throttle for a brief run-up, intending to use full power only long enough to get the heavy cut rolling before backing off. As the locomotive started to move, one foot slipped on the brake pedal. In that moment, the independent brake, the one meant to hold just the locomotive, released its grip. The automatic air brake, which controls the entire train, had not been applied. The locomotive, now at full throttle, began to pull all 47 cars, including the hazardous tankers, out of the yard. No alarms sounded. No safety mechanism intervened. What began as a routine repositioning now had the potential to become a 66-mile emergency. The systems in place, procedures, mechanical interlocks, and safety protocols had all been followed, at least in spirit. But the interaction of small choices and the logic of the controls created a gap no one expected. As 8888 rolled south, the yard was left with a question: how could a simple move turn into a runaway, and why did the safety layers not stop it? Locomotive controls are built on a careful balance of power and braking, especially during yard operations. On the EMD SD42, the engineer manages 3 levers: throttle, dynamic brake, and independent brake. The throttle offers 8 notches, each increasing traction motor output. The dynamic brake, when engaged, reverses the motor's roll, turning them into generators to slow the train without friction. Yet a critical vulnerability lies in the interplay between throttle and dynamic brake. If the throttle moves above run 6, the dynamic brake instantly drops out. This interlock is meant to prevent simultaneous full power and braking, but it creates a brief gap. A sudden shift from dynamic braking to full throttle leaves the locomotive surging forward with no resistance. The independent brake, operated by hand or foot, affects only the locomotive. During the CSX 8888 incident, a slip on the foot pedal released the independent brake just as the throttle reached run 8. The automatic brake, which controls all 47 cars, was untouched. The brake pipe remained at yard pressure, isolated from the rest of the train. No air vented and no brakes engaged on the trailing cars. The result was 3,000 horsepower unleashed, with nothing holding back the train's mass. This outcome was not a failure of machinery, but of logic. The dynamic brake interlock disengaged above run 6. The independent brake, once vented, offered no hold. The automatic brake, never applied, left the train free to accelerate. A single moment exposed a gap in the system, where efficiency and routine left no overlap for error. At 12:35 in the afternoon, CSX 8888 rolled out of Walbridge Yard with no one at the controls. The throttle lever, still locked in Run 8, commanded every ounce of the locomotive's 3,000 horsepower. With the independent brake released and the automatic air brake never applied, nothing stood between the train and open track. The system did not register a fault. No alarm sounded. The logic built into the SD-4E2's control stand saw no reason to intervene, and by its own rules, the train was operating as ordered. Within minutes, the heavy consist surged onto the main line. Trackside sensors clocked the Runaway at close to 30 miles per hour before the first 10 minutes had passed. Data from the event recorder later confirmed the speed increase. At 12:36, 12 miles per hour. At 12:41, 22 miles per hour. At 12:45, nearly 30. The train's mass, 47 cars, including 2 tankers of molten phenol, amplified the momentum. With every second, the distance between the Runaway and the last human touch grew wider. This was not a malfunction. The interlocks and brake logic performed exactly as designed. The independent brake, meant for short stops and yard holds, offered no resistance once released. The automatic brake, controlling the full length of the train, remained idle, its handle untouched. The throttle's command was absolute. As 8888 accelerated, the gap between system design and real-world risk became starkly visible. The train was now a moving hazard, unmanned, accelerating, and invisible to safety systems built to trust the logic of their own controls. It would take several more minutes before anyone beyond the yard realized that a fully powered freight train was barreling south with no one at the helm. If you are interested in how hidden systems and overlooked vulnerabilities can turn routine into crisis, subscribe and follow this investigation as we uncover the deeper story behind the Runaway. There is more to discover about the mechanics, the missed signals, and the lessons still shaping rail safety today. At 1:05 in the afternoon, the CSX Dispatch Center in Cincinnati received an alert. An unmanned freight train was accelerating down the main line, hauling 47 cars, 2 of them tankers filled with molten phenol. Inside the dispatch room, routine dissolved into urgency. Molten phenol, kept liquid only above 40 degrees Celsius, is acutely toxic. If a tank cooled or ruptured, the chemical could solidify, crack the steel, and release a poisonous vapor cloud. This was not just a runaway train, it was a rolling chemical threat, gathering speed through rural crossings and small towns, soon topping 40 miles per hour. Emergency managers across Northwest Ohio activated hazmat protocols. Local fire departments and the Ohio State Highway Patrol began preparing evacuation plans for communities along the projected path. Dispatchers worked with Norfolk Southern to clear the line, knowing a derailment could trigger a disaster the region had never faced. The presence of those 2 phenol tankers changed every calculation. Each minute, as the train's momentum built, so did the risk. The margin for error was razor thin. At 1:30 p.m., CSX dispatchers faced a decision that would shape the rest of the event. With a fully loaded Runaway gaining speed and hazardous chemicals on board, the question was not just how to stop the train, but how to do it without risking a catastrophic spill. Derailment devices, sometimes used in last resort situations, were quickly ruled out. The risk to nearby communities and the volatile phenol cargo made intentional derailment too dangerous. Cutting power to the tracks or waiting for the train to lose momentum were also dismissed. The SD-4E2's throttle, locked in Run 8, would not respond to a remote shutdown, and the open mainline offered no natural choke point. Instead, dispatchers authorized a direct interception. The order went out for the SD-4E2 unit number 7017, stationed at a nearby siding to pursue the runaway at up to 60 miles per hour. The crew, an experienced engineer and a brakeman, prepared for a high-speed chase with the understanding that they would have to catch and physically board the moving train. This approach was not standard protocol, but it offered the only real chance to regain control before the runaway reached more densely populated areas. With the decision made, the catch locomotive accelerated onto the main line, closing the gap as the crisis shifted from a remote emergency to a hands-on rescue. The catch locomotive closed the final gap, drawing to within about 500 feet of the runaway's rear car as both trains matched speed along the main line north of Kenton. With every second, the margin for error narrowed. The two locomotives now moved as a single, tense unit. The brakeman from the catch crew, harnessed and alert, climbed down onto the front platform, waiting for the precise moment. At a steady pace, just under 10 miles per hour, he stepped across the narrow space onto the trailing car of CSX 8888. Once aboard, he moved quickly through the consist, reached the cab, and brought the throttle down from its locked maximum. The independent brake lever was pulled, and air hissed into the cylinders, the first resistance the train had felt in nearly 2 hours. As brake pressure built, the runaway's speed dropped steadily. At 2:20 p.m., after traveling approximately 66 miles, the train rolled to a stop just north of Kenton, Ohio. The physical danger had passed, the line was silent, and the hazardous cargo remained intact. The crisis ended not with a spectacular intervention, but with the measured actions of a crew member who understood the machinery and the stakes. Today, freight trains still move millions of tons through our communities, guided by layers of human judgment and technical design. Every overlooked assumption can slip the system. As railroads automate and scale, the lesson endures. Safety never rests. Keep questioning how the invisible machinery around us really works.